All right, Chan Physics, this is Waves 3, and we're just taking a quick look at some potential questions on the test. So let's see if we can get this to see this a little bit better. Hopefully that's a little bit better. Try one more time. All right, at least in my eyes, that's better. So what we have here is they're asking us for the amplitude, and they want us to use where we see some different letters here. So right here, it looks like they're showing us a half of a wavelength. Here they're showing us a full of wavelength. Here they're showing us from the equilibrium point down to the bottom. And then they're showing us some sort of like full-fledged thing here. So the amplitude, a lot of people think the amplitude is this, but remember the amplitude is 1/2 the high minus the low. So 1/2 the high minus low is this one right here, D. And then the wavelength would be the full crest to crest, C. So let me get out a pencil so that we can focus a little bit better. All right, so we talked about these things where we have wave interactions. So the one that I told you for sure is going to be on there is the one reflection, where it bounces back off, or absorb, where it just disappears. But here's one that is consistent with what you know. If we talk on this side of the room and it goes through an open door, the sound wave will go through and then it will expand. So that's what they're just showing, it's expanding. So it won't just stay just like there, so you can only hear it right here in the door. You'd be able to hear it here, here, or anywhere. And so the sound wave actually expands out through a diffracted spot right there. The one that's really hard to do is convection, like the eyes and stuff like that. So just count on those three. This one right here that we're trying, and then reflection, where the wave would go back off, or absorption, where the wave would just disappear. And so this is why I kind of got this one out right here, because we didn't have time to talk about what will happen to the wave when it goes through like a solid material. Will it spread out? Will it get slower? How to draw that? So don't worry about that one. All right, and the last one is how many nodes, antinodes, and waves do we see in this? So it looks like the fourth harmonic, 1, 2, 3, 4. So there's 1, 2, 3, 4, 5 nodes, and 1, 2, 3, 4 antinodes. And then remember that this is one full wave and this is a second full wave. So there's 2 full waves. All right. So now we're going to go down to this idea again of figuring out the harmonics from just a limited amount of numbers. So usually they'll give us the fundamental frequency. So here, the fundamental frequency, the one that drives the first harmonic, this is the first harmonic, is 22 hertz. Okay. It's fairly easy to name our harmonics because 1 bump, 2 bumps, 4 bumps, 7 bumps, right? So those are pretty simple. And normally what we'll do is they'll tell us how long the string is. So the string from here to here. So picture the thing that I had up on in the front of the classroom. We had a string, and we had this side was being driven by the wave generator, and this side was tied off. And so the total string length they're telling us is 5 meters. And so since this is only half of a wave, we would take 5 meters divided by 0.5, and we get a wavelength of 10. So that filled out the first 3, and then we have to remember the velocity equation. Velocity equals the wavelength times the frequency. So V equals this times this. So 10 times 22 is 220. All right. Once we've got one, that's pretty simple to get the rest, because the velocities are going to be the same. Okay, the velocity never changes. And so then once we get that, we can just say, okay, well, how do we find the harmonic frequencies? So we said there was an equation, I'll write it down right here, that the F of any number is equal to the fundamental times the number. And that's kind of hard to remember what that means. But that means that if we're trying to find the second frequency, the second harmonic, we just have to take the fundamental, 22, and multiply by 2. So 2 times 22 is 44. And here, if we wanted to find the frequency that would drive the fourth harmonic, well, it's just 4 times 22, or 88. And here, 7 times 22, right, will get us that frequency. Once we have that, we have 2 things in our wave equation. Remember, V is equal to F times wavelength. And so if we know the velocity, 220, and we know the frequency, we can always find the wavelength. Okay, but there's other ways to do the wavelength. If we know that this is 5, right, this is 5 meters, we can always get the wavelength, because if this is 5 and there are 2 full waves, then it's 2.5. If this is 5 and there's 1, 2, 3.5, 5 divided by 3.5 will get us the wavelength. So we see right here, this is 1 full wave. We know that this is 5 meters. That's 5. So there's many, many different ways to do it. And so you can see this fundamental equation. The fundamental of any number is equal to the fundamental frequency times, I'm sorry, I said that wrong. The frequency of any harmonic number is equal to the fundamental times the number. So let's say I want to find this one. They're saying they want to know the 5th harmonic. So I'm just going to take the fundamental frequency and multiply it by 5 to get what's going to drive that 5th harmonic, the one that looks with 5 bumps on it. All right, the last thing is this idea called superposition. And what this was is this is all the stuff coming together into one idea of whether or not there's constructive interference or destructive interference. So in this instance right here, we have a wave that's in solid line, and there's a second wave that's in dotted line. And we want to know what it would look like for those 2 waves if they were together. And so what we would see is that we just see that they would be building on each other on both sides, right? They would add this up. So this one right here would add to this, and we see a much bigger wave, all right? So then the second one right here, we have waves that are out of phase. The dotted line ones are going this way, but the other ones are going the opposite. But the dotted ones are half the size of the solid one. So we'll only be able to destroy half of this wave with the ones out of sync. So we see a smaller wave than we did over here. And then this one right here, we have a perfectly timed destructive wave. So this one's going up while this one's going down. And so what will this end up doing? This will end up looking like nothing. And so it will be completely destroyed. So hopefully you guys got those things. We'll have time over the next Friday and Monday to get everything ready before we go to the quiz on, or the test on Tuesday. So make sure you get this down, and then we'll talk to you on Friday.